valence bond theory. So I think we've seen that Lewis model, although it's user-friendly, is an oversimplification. There are some things it can't handle. It can't handle resonance structures. It doesn't do well with the expanded and incomplete octets. It's like, hey, wait a minute, what's up with those? So to get to a more advanced bonding theory, we use quantum mechanics. So the quantitative approaches to predicting properties of molecules are going to look at things like bond length, strength, molecular geometries, and dipole moments. There's more than one theory. We're going to look at two of them, but not in a quantitative manner. We're going to look at them in a qualitative manner. So we'll get kind of deep into valence bond theory. The next section is about molecular orbital theory, and we'll just give you a brief introduction to that. Okay, so quick review of quantum mechanics. So electrons reside in quantum mechanical orbitals. Those are localized on individual atoms. So that's the S, P, D, and F atomic orbitals. So we can hybridize atomic orbitals, taking different types of orbitals like S and P orbitals and hybridizing them, blending them into new atomic orbitals. Valence bond theory treats chemical bonds as being the overlap of orbitals. So as two atoms approach each other, the electrons and nucleus of the one atom are going to interact with the electrons in the nucleus of the other atom. There's going to be attractions and repulsions. Valence bond theory looks at the energy changes that result from those interactions. If the interactions result in a net lowering of energy, then a bond forms. If it does not, then a bond will not form. So you have two atoms approach each other, and they're just not real attractive to each other. Them being close does not make things lower in energy, and so they will go on and go away from each other again. If two atoms come together and the overlap of them, their interactions causes them to be more stable, lower in energy, then a bond forms. So this is a graph looking at the energy as two hydrogen atoms approach each other. So this would be zero distance between the nuclei of the hydrogen atoms, and this would be a large distance. So zero energy. When these two atoms are far apart, there is no energy as a result of their interaction. There's not an attraction or a repulsion. As these come closer together, there's a little bit of an interaction. There's a stabilization, a lowering of energy. They're like, oh, I like you. Yeah, I'm attracted to you. They get closer together, the energy goes down. They get closer together, the energy goes down a little more. At this point, they've reached this best distance. And you've probably experienced this with people in your life. There's people that, you enjoy interacting with, but if they get too close, then it's not so nice anymore, right? Or you run into one of those close talkers that gets in your personal space and you just keep backing up, right? So we go past this point, and now the hydrogen atoms are becoming increasingly uncomfortable with each other. And if you get them too close together, then they're actually going to repel each other. So just like a ball, if you had a ball here and you let it roll, it would roll down and maybe go up a little and wiggle around a little, and it would settle at this lowest place. These two atoms, they're going to come together and move back and forth a little until they find that perfect place, that sweet spot, where the energy is the lowest, and they'll form a bond. This distance where the energy is the lowest is the bond length, and this drop in energy is the bond energy. Any questions? So the interaction energy is usually negative when the interacting atomic orbitals contain a total of 2 electrons that can spin pair. Remember we drew orbital diagrams and we had the arrow going up and the arrow going down? And in the quantum hotel I said you can't have 2 electrons sleeping next to each other head to head. They're going to, one of them's going to sleep upside down because they don't like sharing a bed. So these interactions will often come from 2 half-filled orbitals. So in that hydrogen example, you've got one hydrogen with a half-filled 1s orbital and the other hydrogen with a half-filled 1s orbital. You overlap those s orbitals, and now you've got 2 electrons in there, and one of them can flip and they'll spin pair, and that's how they can be in the same orbital together. That's usually what happens. Sometimes, though, you can get a filled orbital from one atom overlapping with an empty orbital from the other. That's called a coordinate covalent bond. That's less common, but it does happen. So when you've got 2 atoms with half-filled orbitals approaching each other, the orbitals will overlap, and the electrons are going to line up with opposite spins. So just to summarize what we've talked about so far, the valence electrons of atoms in a molecule reside in quantum mechanical orbitals. Chemical bond results from the overlap of 2 half-filled orbitals with spin pairing of the 2 valence electrons. And then the geometry of the overlapping orbitals is going to determine the shape of the molecule. So let's look at how this would work. So here we have dihydrogen sulfide, or hydrosulfuric acid. We've got 2 hydrogen atoms and we've got a sulfur atom. So we can look at the valence electron diagrams for these atoms. So for hydrogen, it has 1 electron in the 1s orbital, and the other hydrogen has 1 electron in a 1s orbital. For sulfur, we're only going to look at the valence electrons. This is valence bond theory. Pointer's gone. Valence bond theory. We're looking at the overlap of valence electrons. So sulfur has 6 valence electrons, and there's going to be 2 in the 3s, and there's going to be 4 in the 3p subshell. So 2 of those p orbitals are half-filled and 1 is filled. Everybody okay with that? So what we imagine happening here is that this half-filled orbital from sulfur can overlap with this half-filled orbital from hydrogen. Those electrons can pair, and that's going to form a bond. So that's this bond here. We've got this is a p orbital from sulfur overlapping with an s orbital. And the other half-filled p orbital can overlap with the s orbital from another hydrogen. And so that's this one right here. Remember, those p orbitals are aligned along the x, y, z axes. So does that kind of make sense? Yes?
So we're just bonding the half-filled orbitals with the previous s orbital?
You're overlapping the half-filled orbital on one atom with a half-filled orbital on another atom. Yep. So this is all very nice. Unfortunately, it doesn't quite match up with what we observe. So this would predict that the bond angle here would be 90 degrees, right? Because of the orientation of those p orbitals. So if you have 2 p orbitals overlapping, the bond angle is going to be 90 degrees. Vesper theory, which we just talked about with the balloons, let's draw the Lewis structure of this. So here you have sulfur, and you've got a hydrogen, and no, that's too big. And there's 2 lone pairs on the sulfur. So this is a lone pair on the sulfur atom. This is a lone pair on the sulfur atom. And these 2 orbitals are, the electrons in those orbitals are the ones that are being shared with hydrogen. So if we look at this, we look at the central atom as 4 electron groups. That would be tetrahedral, right? And then 2 of those are lone pairs, so we'd say that this is a bent molecule. And the angle here should be less than 109.5. Not sure exactly what it is, but less than 109.5. Well, if you actually measure it, we find out that the bond angle is 92 degrees. Well, that's less than 109.5, right? So like, it's a little higher than 90, but, you know, things bend around, right? Any questions so far? Yes?
How do you, like, what to spot this? Is it by bond or is it by shape?
How do you spot what?
That they're the half-filled orbitals.
Half-filled orbitals? So this part comes from drawing the orbital diagrams based on the number of electrons in the atom. And so you would find out how many half-filled ones there are by actually drawing out the diagram. Yeah. Any other questions? Yeah.
Do we have to know the angles?
Do you have to know the angles? I would expect you to be able to tell me that the bond angle, predicted bond angle on this from Vesper theory is less than 109.5. It's a tetrahedral shape because of the 4 groups, the electron geometry. The lone pairs are more repulsive. So the ideal geometry would be 109.5. The lone pairs are going to cause the hydrogens to squeeze together. How much? Don't know. That's beyond the scope of Chem 1A. Okay, let's look at another one. Let's look at carbon and hydrogen. Waiting for my iPad. Oh, there it is. Okay. So let's look at carbon and hydrogen. So here we have an orbital diagram for hydrogen. Easier to draw than it is to say, apparently. And here's an orbital diagram for carbon. Carbon has 4 valence electrons. And so we learned that it will fill up this 2s orbital first because it's lower in energy, and then the next 2 electrons will go into the 2p orbitals. And so we have 2 half-filled orbitals here. So what we've learned so far is going to predict that this orbital will overlap with with a hydrogen. And then we need another hydrogen atom. And this orbital is going to overlap with the half-filled orbital on another hydrogen atom, just like with the sulfur. And so here is the half-filled orbital for carbon overlapping. This is a p orbital overlapping with the s orbital. And here is another p orbital overlapping with an s orbital for the hydrogen. This blue one in the center is this s orbital that's got a pair. The third p orbital isn't shown because it's empty. Yes?
In methane, would those hydrogens take up that last?
Well, we'll get to that. What's happening with methane. So our theory so far predicts that carbon and hydrogen would bond to form CH2, and that the bond angle here would be 90 degrees. But what we observe is that carbon and hydrogen form a compound with 1 carbon and 4 hydrogen atoms. We do not observe CH2 as a stable molecule. And the bond angles here are 109.5 degrees. So something is missing with this theory, right? And so the question, well, do those take up the other orbital that's here? Yes, it's a little more complicated than that. So we've been looking at the orbitals on the carbon atom in a molecule being the same as the orbitals on a carbon atom that's all by itself. That's not necessarily true. The orbitals can change when the carbon atom becomes part of a molecule. So we call that hybridization. So a hybrid is something that brings two different things together. A hybrid vehicle can run on electricity and gasoline, right? If you hybridize plants, you're taking two different varieties of a plant and coming up with one that's a combination. So for these orbitals, hybridization is a mathematical process, sort of like averaging, but we've talked about orbitals, and they are these very complicated mathematical wave functions. So the math is pretty hairy here, and we don't have to deal with it, thank goodness. But you take these two wave functions and you combine them together. This is going to form hybrid orbitals. So it's a combination of different kinds of orbitals. These correspond more closely to the actual distribution of electrons and molecules. These orbitals are still localized on the atom, but they're going to have different shapes and different energies than the regular atomic orbitals. What hybrid orbitals do is they minimize the energy of the molecule by maximizing the overlap. So by mixing up, hybridizing the orbitals on that atom, we can maximize the overlap with other atoms, and that will cause it to be lower in energy. The reason that we get better overlap here is because the electron probability density, instead of like for a p orbital where it's evenly distributed on opposite sides of the atom, when we hybridize the orbitals, now it's lopsided, it's more on one side than the other. And so we can get better overlap because between two atoms, you know, if you think of yourself as the carbon and you're wanting to overlap with hydrogen, the hydrogen is on one side of you. And if you've got a p orbital, you've got half the p orbital overlapping with the hydrogen, the other half is on the other side, right? You can't get really good overlap that way. So when we hybridize, we get more lopsided orbitals, and so then we've got more probability density on the hydrogen side in the bond. Hybridization does require energy. It doesn't just happen by itself. It's sort of like, having a business, right? And maybe, you want to paint the outside of the building, or you want to add a fancy new sign or a new soda fountain or something. You have to make an investment in that, right? And good business says, well, I'm only going to shell out the money for this if it's going to increase my business, right? If you have an employees-only restroom and you shell out thousands of dollars to make this bathroom just gorgeous, but none of your customers ever see it, is that going to increase your business? No. It might make your employees happy, but it's not going to increase your business. So that's not a good investment. You're not going to do that. That's why a lot of employee bathrooms are just really not that nice. But, painting the outside of the building or advertising might be an investment that's going to bring you more business. So overall, you're going to end up with money, even though you had to spend some. So the same thing happens here. That hybridization requires an investment of energy, and it's only going to happen if you get a big payback when that bond is formed. So what we're going to look at is the hybridization of atoms that are on the inside of a molecule, and we're going to assume that any atoms in the terminal positions are unhybridized. It makes things simpler. And we do know that atoms that form more bonds are more likely to hybridize. So that's sort of a justification for ignoring those terminal atoms. They have one bond, and so they are less likely to hybridize. So general statements about hybridization. The number of standard orbitals that you're hybridizing always equals the number of hybrid orbitals that you get. So if you start with 3 orbitals, you're going to end up with 3 orbitals. So conservation of orbitals. The particular combination of the standard orbitals that you're putting together in this hybrid is going to determine the shapes and the energies of the hybrids. And what type of hybridization occurs is whichever one gives the lowest overall energy. So all of that involves some very hairy calculations, and we're not going to go into that. So what we're going to do is we're going to use Vesper theory electron geometries to help us to predict what the hybridization of a given atom is. Okay, so let's go back to that carbon-hydrogen issue where where Vesper theory and the simple version of valence bond theory said we get CH2 with a bond angle of 90 degrees. So here we have the standard orbitals for carbon. Now we're showing them in a more expanded type of orbital diagram. So there's the 2s orbital with 2 electrons in it, and here's the 2p subshell. 2 of those orbitals have 1 electron. That's the standard atomic orbitals. When we hybridize those, we can take these p orbitals, all 3 of them, and the s orbital, kind of throw them in a blender and mix them up, average them out, and make them into 4 hybrid orbitals. The 4 hybrid orbitals are all going to be the same in energy. And the energy of these orbitals is an average of those, right? It's going to be less than the highest energy ones and higher than the lowest. And so they're going to come out equal. Now we have 4 degenerate orbitals. They're all the same energy. So if I don't say anything, he won't honk his horn again. In the quantum hotel, what this corresponds to okay, in the quantum hotel, I talked about an s orbital being a room with 1 bed, and the p sublevel was a room with 3 beds, right? And it costs more to sleep in this room than in this room, just because that's how it's set up. So making the hybrid orbitals here is a bit like remodeling the hotel. So the S room and the P room were right next to each other. So we're going to remodel it. We're going to break down the wall between them. And now we have 1 big room with 4 beds. Can I charge more for the bed that used to be in the P room but now is in the same room with the S bed? No. We're going to charge the same for all of them. And so that's what this is like. And then you've got your 4 electrons coming to stay in this room, and they can each have their own bed, right? They can each have their own orbital. You with me so far? Okay. Now, that does require an investment of energy to create this from these guys. So let's look at illustrations of these orbitals to see what it might look like in 3-dimensional space when these get mixed together. So we have an s orbital, and we have 3 p orbitals. One's along the x-axis, one's along the z-axis, one's along the y-axis, right angles to each other. You put all of these together, and you average them out, and what you end up with is 4 identical orbitals, but they're now spaced out equally in 3-dimensional space. Because we're combining this S with P's that are symmetrical with a lobe in the middle, what we end up with is something that looks a little more like a turkey drumstick, where you've got a big end and a small end. So there's a node at the nucleus, but one side is larger than the other. And these are going to be spaced out, not along X, Y, Z axes, because that's 3. We got to get 4 things spread out, and 4 things make a tetrahedron. So they're going to point to the corners of a tetrahedron. Here we're going to show them all together, and when we show all of them together, what we usually do is this little piece on the other side, we leave that out. because this picture is complicated enough. We're just going to focus on the large lobe, but there is a small lobe on the other side. But it's the large lobe that's going to overlap with another atom's orbital. Any questions? So we hybridize the orbitals on the carbon. It's the valence orbitals. So now we've got 4 orbitals that are the same, and instead of them being S or P, we give them the name sp3 because it's formed from 1 S and 3 P orbitals, right? So we're not trying to be tricky here. So the electrons are going to spread out. So now carbon has 4 half-filled orbitals. So if we bring in a hydrogen atom, there's a hydrogen atom with its half-filled s orbital, then one of these orbitals can overlap with that hydrogen atom. This next orbital can overlap with another hydrogen atom. This one can overlap with a third hydrogen. This one can overlap with a fourth hydrogen. And so here we have an illustration of that. In the purple, because red and blue together make purple, right? So the purple are hybrid orbitals. We have these 4 purple hybrid orbitals that are oriented to the corners of a tetrahedron, and each of them can overlap with a half-filled s orbital on a hydrogen atom. Does that make sense? So then we get our predicted result is equal to our observed result, that CH4 is the simplest molecule that forms between carbon and hydrogen. And what's the geometry of this? It's tetrahedral, which is what Vesper theory predicted, but Vesper theory can't explain why it's that way. It just says, yeah, it's going to be tetrahedral. Any questions? What about a lone pair? Well, one of those hybrid orbitals could have a lone pair in it. That pair of electrons would just not be bonding with something else. It'd just be a lone pair. So if we look at hydrogen and nitrogen, let's see here. So nitrogen, if we form sp3 hybrid orbitals for nitrogen, how many valence electrons does nitrogen have? 5. So if we're going to put electrons into these hybrid orbitals, we're going to do it the same way we did with regular orbitals. Singly first, 1, 2, 3, 4, and then that 5th one has to pair up with somebody. So here we have the valence hybrid orbitals. So we have a lone pair and we have 3 half-filled orbitals. Each of these half-filled orbitals can overlap with the half-filled 1s orbital of hydrogen. And the 4th one is got a lone pair in it, and it's just going to stick out there like a sore thumb. So these hybrid orbitals would have an arrangement where they are tetrahedral with 109.5 degree angles, right? But this lone pair causes the angle to be a little different. The actual angle is 107, and that's a little closer to the unhybridized p orbital. The hybridization of these orbitals is less than complete because of the lone pair. So the lone pair is messing up the hybridization a little bit. So instead of being equally spaced in a tetrahedron, it's a little tweaked because it didn't quite go all the way. Any questions? Okay, what if you just take 2 of the p orbitals and the s orbital and hybridize them. So we're going to take the s orbital and 2 p orbitals and mash those together. We're going to end up with 3 identical orbitals, equal energy, and we're going to give them purple because they're red and blue together. Now we're going to call these sp2 because it's an s and 2 p orbitals that have combined. There are 3 of them because we took 3 orbitals. And what happens to this unhybridized p orbital? Nothing. It's still there. And so here it sits, unchanged, unhybridized p orbital. So let's look at how this happens. So there we've got the s orbital, and we've got 2 p orbitals. If we're just looking at 2 p orbitals, then we can look at it in 2 dimensions instead of 3, and it's easier to imagine. So we're going to combine these together. We're going to end up with 3 identical shapes, and we're going to get this drumstick shape again, but now these are going to be oriented at the corners of a triangle. And so putting them together without showing that small lobe, we'll get this. What are the angles between those hybrid orbitals? 120, right? So let's look at H2CO. This one has sp2 hybrid orbitals. So here's, not there, here's carbon. Its atomic orbitals, a 2s and 3 2p orbitals. It's got 4 valence electrons, and so they'll be like this. Now we're going to take the s and 2 of the p's and hybridize those, and then we've got this p orbital also. The p orbital is higher in energy, but there's a bonus. So we can give each of these electrons their own space. So now we've got sp2 and this p orbital. We have hydrogen and we have oxygen that are bonding to the carbon. So the Lewis structure here's the Lewis structure. So we can get overlap of s orbital with that hydrogen, and this s orbital in the hydrogen overlaps with one of the hybrid orbitals. This one overlaps, this hybrid orbital overlaps with another hydrogen, and then this one overlaps with one of the half-filled p orbitals on the carbon. Now what about, let's make that clear. What about this guy? What about this unhybridized orbital and this one? Only one of the oxygen orbitals is overlapping with the hybrid orbitals. We've got this one left over and we've got this one left over. Those 2 unhybridized p orbitals are going to overlap with each other. And that's what's going to form this double bond. This is like really bizarre balloon art, right? Okay, so what do we have going on here? Here's the carbon, and the purple is the sp2. sp2, there's 3 orbitals, and they're spread out in a triangle. One of those overlaps with a hydrogen, one of those overlaps with another hydrogen, one of them overlaps with the unhybridized p orbital on the carbon. The oxygen, right? We also have a p orbital on the p orbital on the oxygen. So there are 2 half-filled p orbitals. So one of them is here, and the other one is here. And then we have the unhybridized p orbital on the carbon that's also half-filled. and these can overlap, they're going to overlap side to side. So the lobes on the top overlap, and the lobes on the bottom of this plane overlap. Do you think that's as good of an overlap as this end-to-end one? It isn't. It's sort of strained, right? Because you got this guy, and he's like leaning over here and leaning over here, and they're trying to overlap, but it's kind of hard. This is called a pi bond, this side-to-side overlap, and the end-to-end overlap is called a sigma bond. So this is a sigma bond, that's a sigma bond, that's a sigma bond. This is a pi bond. So it kind of looks like the letter pi. Use your imagination a little bit. Pi. If we look at the molecule from the end, look from the oxygen down to the carbon, what we would see for this sigma bond is it would look like a circle, right? Looking down this end, we'd see this lobe and that lobe, and they would line up with each other, and then we wouldn't even see this because it's all behind. It's just like looking at the end of a cylinder, right? That's a sigma. It's a circle. It's symmetrical. The pi bond, we're going to see something like this, where there's going to be part of it above and part of it below that sigma bond. So the sigma bond is end-to-end overlap. It's symmetrical. The pi bond is not symmetrical. Any questions? So let's look at that a little more. So here we have two half-filled p orbitals, and those can overlap side to side to form a pi bond. Or if they're oriented properly, they can overlap end to end and form a sigma bond. Just how are they overlapping? Could you have a pi bond between a p orbital and an s orbital? No. This pi bond, we've got overlap of these two lobes and these two lobes. An s orbital is only one lobe, if you will. And so it can't form this double overlap. Now, what can be a little disturbing, but you have to remember the electrons are disturbing. Quantum mechanics is very disturbing. This looks like two bonds, doesn't it? Doesn't it? There's two things there, right? This is a single bond. There is one pair of electrons that's occupying both sides of this at the same time. And that's because this is essentially a standing wave. And so the electrons are on both sides at the same time, without being in the middle at all. So this is one pair of electrons, that's one bond. This is one pair of electrons, one bond. So here we have the Lewis structure for that molecule, a double bond between the carbon and the oxygen. And so we've got the sp2 hybridization on the carbon and then an unhybridized p orbital. The oxygen, that's a terminal atom. It's only connected to one other atom. And so we're going to assume, for simplicity's sake, that it doesn't hybridize at all. And so it's just got these two half-filled p orbitals. It also has a full p orbital and a full s orbital. We're not going to show those. Those would be the lone pairs. So we have an overlap end-to-end and a side-to-side overlap. And so we can label these with a notation that explains what they are. So these two bonds are sigma bonds. So sigma and then a colon. And we've got C in parentheses sp2. So that's the type of orbital on the carbon that's overlapping. Dash the other atom, hydrogen, and the hydrogen has an s orbital. This bond is also a sigma bond, an end-to-end overlap. where we have carbon contributing an sp2 hybrid orbital overlapping with oxygen's p orbital. And then the pi bond is between a p orbital on carbon and a p orbital on the oxygen. Any questions? So we get more insight with valence bond theory than with the Lewis model. The Lewis model says, yeah, there's a double bond between carbon and oxygen. Valence bond theory says that double bond is not two identical bonds, it's two different bonds. It's one sigma bond and one pi bond. And what we observe is that the bonds between the carbon and oxygen are different. You can break one of the bonds without breaking the other one. The pi bond is easier to break because it doesn't have as good overlap as the sigma bond. The sigma bond is stronger. Rotation about these bonds is different. In a single bond, you can get free rotation around this because as you're twisting this guy, this can just rotate. So that's a little bit like making a bond by sticking your index fingers together end to end. And you can turn this hand around and still have your fingers touching. In the double bond, where you have a pi bond and a sigma bond, that's like taking two fingers on your left hand, two fingers on your right hand, and touching them to each other. And now you cannot rotate one of your hands without breaking one of those contacts of the fingers because you can't get the rotation now. And this works out well with the models. So let's make one of those real quick. Maybe it's not so quick. Someday I'll think ahead and have these ready to go. Where are the excitement of these at? Okay, so here's a model of this molecule here. So the black balls are the carbons, the white balls are the hydrogens, and the green balls are the chlorines. And if I try to rotate this, I've got this double bond here, I can't rotate it, right? It does not twist. So there are actually two different molecules here because of the double bond. We can have it this way with the chlorines on the same side, or to make the other one, you actually have to break bonds. You can have another molecule, same kinds of atoms, but now the chlorines are on opposite sides of the double bond. So those are two different molecules. They have two different sets of properties. If I make this into that first one, using single bonds, okay, so here's that first one. Now I've got the two chlorines down here, and I've got hydrogens up here, and a single bond between the carbons. I can turn the one, and I can rotate this around. And in actuality, this does happen, and so a molecule like this has free rotation, and you can find it in many different combinations. Okay? Both of these, well, yeah. So here we're looking at those same molecules, but looking at space-filling models. So the first one is 1,2-dichloroethane, has free rotation, and so you can rotate this around so that the chlorines are on opposite sides, but these are actually the same molecule. They interconvert, they go back and forth. You can make this one and back and forth without breaking any bonds. It's the same molecule. These two molecules are different. This is cis 1,2-dichloroethane, and this is trans 1,2-dichloroethane. Trans because the chlorines are on opposite sides, cis, they are on the same side. You cannot convert this one into that one unless you break a bond. You could break you could break the pi bond here, rotate it and reform the pi bond, or you could break a hydrogen bond and the chlorine bond and switch those, but you can't convert from one to the other without breaking bonds. They are different molecules. Any questions? This is the sort of thing that organic chemists care about a lot. Okay, what if we just take the s orbital and one of the p orbitals? So a red one and that's blue. A blue one and a red one, and we get two purple ones, and we're going to call those sp because it's an s and a p. So sp orbitals, and then these two p orbitals that are unhybridized just stay there. So here's an s orbital and a p orbital. You hybridize those, you're going to get two orbitals, one with the large lobe on the right side, one with the large lobe on the left side. And we show them together. It looks a lot like this p orbital, doesn't it? But it's different. There is a small lobe on the other side, and we've taken these two and made these two. They're perpendicular to each other. So acetylene, it says draw the Lewis structure. That actually is the Lewis structure, pretty much. There's no lone pairs. So what's going to happen here is we've got the hydrogen and we've got the carbon, and we're going to hybridize this s orbital and one of the p orbitals. So we're going to have hybrid orbitals for sp. Then there's two p orbitals left over. So we'll put those 4 electrons each in their own orbital, and we can predict that the carbon is going to make 4 bonds. This sp hybrid orbital can overlap with the hydrogen. End-to-end overlap, a sigma bond. This sp orbital, hybrid orbital can overlap with a second hydrogen. What's happening in the middle, wait a minute, back up. That would be talking about hydrogen with 2 carbons on it. Carbon with 2 hydrogens on it. You get the idea. We need a second carbon. Let's just draw all of them out here. So there's sp and there's 2p. And we've got another hydrogen as well. Okay, now we can talk about this a little better. So one of these hybrid orbitals will overlap with an s orbital on the hydrogen. And on this other carbon, one of those will overlap with the hydrogen. Now that leaves a hybrid orbital on each of these, and so those will overlap, the carbon with the carbon, and that will form a sigma bond between the 2 carbons. Then we have 2 unhybridized p orbitals. So those are sticking, if these hybrid orbitals are along this axis, then the p orbitals are going up and down and in and out. And so these 2 can overlap. That's going to form a pi bond, and the other 2 can overlap, and that's going to form a pi bond. So these are sigma bonds and sigma bonds. So this triple bond is a sigma bond and 2 pi bonds. You ready for the picture? You thought the other one was weird? Right? That could be fun as like a pool float or something, maybe. I don't know. So here's carbon. It had sp hybridized orbitals. It had 2 sps, right? So one in this direction and one in that direction. One of them overlapped with hydrogen. The other one overlapped with an sp hybrid on this carbon. So this bond here in the middle is sigma CSP CSP. Overlap to the hybrid orbitals. This carbon, its other hybrid orbital, overlaps with hydrogen. So the hydrogens and the carbons are all in a line. And then the p orbitals are perpendicular. So we've got p orbitals going this way on both carbons. They'll overlap side to side, forming 1 pi bond. And then we've got the vertical ones overlapping side to side, and they'll form a 2nd pi bond. So we've got a sigma bond and 2 pi bonds making up this triple bond between the carbons. Valence bond theory agrees with VSEPR theory that this molecule is linear. Carbon, hydrogen, all lined up together. And we can do that with the model kit as well. We'll use these flexible connectors so that we can make 3 connections between 2 atoms. You want to get your finger stuck in there. And then there's a hydrogen on each end. So it's linear. So we learned in the Lewis model that elements in the 3rd row or below can exhibit expanded octets. Below meaning physically below on the periodic table. 3rd row, 4th row, 5th row, etc. In valence bond theory, this corresponds to hybridization including the d orbitals. The energies of the 3d orbitals are similar to the 3s and the 3p. And so we can combine these together. So now in the hotel, we're taking those rooms and we're knocking out 2 walls and we're going to combine things. So we can combine the S with 3 P's and 1 of the D's. You can't do an S, 2 P's, and a D because that P room is in between the S room and the D room. And so if you're going to go into the D room, you could move the wall over like here and keep 4 beds in the D room, moving the wall over, and so you're going to have 1 bed in this new combined room. But you can't exclude any of the p orbitals. So an S, 3 P's, and a D, we call that an sp3d. Now we have 5 orbitals that are the same energy. And the d orbitals remain unhybridized. So you put those together and you end up with a shape like this. That looks a lot like those balloon shapes I made the other day, right? This is 5 things spreading out in 3-dimensional space. It's trigonal bipyramid. So arsenic pentafluoride does this. The arsenic will do the sp3d hybridization so that it has 5 equivalent orbitals. And each of those orbitals will make a sigma bond with 1 of the orbitals on the fluorine. And so we get a trigonal planar structure. So they're overlapping with a p orbital on fluorine. What if we take 2 of the d orbitals? Well, then we've got sp3d2. Now there's 6 of them, and they're going to make an octahedron. So here's sulfur hexafluoride. The sulfur will get into its d orbitals and hybridize so that it has 6 degenerate orbitals. Each of those spread out in this octahedral shape will overlap with a p orbital on a fluorine. So why can't oxygen do this? Where are oxygen's valence electrons? In the 2s and the 2p sublevels. In order to expand, there would have to be a 2d orbital. There isn't one. The next one is 3s. That's a higher principal energy level that's not accessible. So that's why period 1 and 2 can't do expanded octets. It only starts at period 3 because those guys have access to the 3d orbitals. And we're not going to go any farther with including more of the d orbitals. Okay, so how do you know what hybrids it's going to form? Well, you could do calculations and figure out which one's going to have the lowest energy. That's too far for us. We're going to go with good enough for Chem 1A. We are going to assign the hybridization scheme based on the electron geometry of the interior atoms. It's not 100% accurate, but it's good enough. And so that's what we're going to do. So we have to understand Vesper theory. That's why we talked about that first, because Vesper theory is going to help us predict the hybridization. So we look at the electron geometry. The number of electron groups on the central atom tells us what the hybridization is. Excuse me while I write on my fingers. It's tricky because I'm left-handed and I need to write on my left hand. So I'm writing an S on my index finger and P's on the other 3 fingers. Okay, so you've got 2 electron groups. 1, 2, sp, hybridization. So if you've got 4 electron groups, 1, 2, 3, 4, sp3. You like that? What if you have 6? 1, 2, 3, 4, 5, 6. sp3, d2. So you just count. How many electron groups do you have? That's how many hybrid orbitals you need. You start with the s. There's only one s. You go into the p's up to 3. That's all the orbitals there are. And if you need more, you go into the d's. And you're very welcome to write on your fingers. This isn't cheating to come in with S, P, and D on your fingers. Okay, so set of instructions for writing hybridization and bonding schemes. Start off with the Lewis structure. Use Vesper theory to predict the electron geometry. What you're doing is you're looking for how many electron groups. Okay? You select the correct hybridization based on the number of electron groups. Write letters on your fingers and count if you need to. Then you sketch the molecule, starting with an interior atom and its orbitals, and show how that overlaps with the appropriate orbitals on the terminal atoms, and then you label everything using sigma or pi notation followed by the type of overlapping orbitals. Clear as mud, right? Write a hybridization and bonding scheme for XeF4. What do we have to do first? Lewis structure. Got to do the Lewis structure. Okay, so I feel like blue. Put Xe in the middle, and it's got 4 fluorines. So we'll bond those. And then we have to look at number of valence electrons. So we've got 4 fluorines. They each have 7 valence electrons. And how many valence electrons does xenon have? 8. So we've got 28 plus 8 is 36. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Where do the others go? Central atom. 34, 36. Xenon is a big boy. He can expand his octet. So that's step 1, Lewis structure. Now we look at the central atom and ask ourselves, how many electron groups? 6. We got 6 electron groups. Yeesh, that was fat. 6 electron groups. So what's the hybridization? 1, 2, 3, 4, 5, 6. sp3d2. sp3d2. Now this is the part that's kind of tricky. Drawing this stupid thing. The three-dimensional drawing, it can be difficult. Okay, so we're just going to do the best we can. So here's our xenon. And I'm going to use purple for these hybrid orbitals. The 6 groups get away from each other like those 6 balloons, and they're going to look like the 6 balloons. It's going to make an octahedron. So we've got 1 going up and 1 going down, and then we've got 4 around the middle. So this one is going kind of behind, this one's sort of coming in front, that one's sort of behind, and this one's sort of in front. I got too many tetrahedrons. Come on. Well, you get the idea. It didn't work so well. So each of these orbitals has 1 electron in it. No, that's not true. Let's look at Xenon's electron diagram. We don't have to do this, but I think it's helpful. So there are 8 valence electrons, right? So the normal arrangement for a xenon atom is like this, where we've got the S and the P, and the D's are empty. When we hybridize this, we're going to end up with 6 that are equivalent. sp3d2, and then there's some d orbitals that are left by themselves. Xenon has 8 valence electrons. 1, 2, 3, 4, 5, 6. The last 2 have to pair up. 7, 8. So we've got 2 that are lone pairs and 4 that are going to make bonds. So I'm going to put a lone pair up here just as a starting point. Where's the other lone pair going to go? The opposite side. Lone pairs are more repulsive. They take up more space, so they need extra room. So we're going to put those opposite of each other. And then we're going to put in our fluorines. We've got 4 fluorines. And they're going to overlap. Well, I should have done this. So each of these orbitals has 1 electron to share. If we look at fluorine's orbital diagram, S and P, fluorine has 7 valence electrons. It has 1 half-filled p orbital. And so that's what it's going to overlap with the hybrid orbitals on xenon. So here we've got another fluorine, and a fluorine out here. Fluorine over here. And fluorine's contributing an electron, so all of these are going to have pairs. That makes sense? You have to use your imagination a little bit. How do we name this? What kind of a bond is this? What kind of an overlap? End to end or side to side? It's end to end. So that's a sigma bond. So this type of bond is going to be a sigma bond. And what's overlapping to make that? On the xenon, what is the name of this kind of orbital? sp3d2. And on the fluorine, what do we have? A p orbital. So we've got this p orbital, half filled, overlapping with one of these half-filled sp3d2 orbitals. And that's going to be the same for all four bonds, right? They're all the same. So we just have to write that out once. What's the shape of this molecule? I'm hearing tetrahedral. Does that look like a tetrahedron? Octahedral? Well, the electron geometry is octahedral, but the molecular geometry, square planar. These are all in a square plane, looking a lot like this, with these guys going up and down out of the plane. Any questions? Isn't this fun? Let's do another one. HCN. Oh, we've got to start with the Lewis structure. So we're going to put carbon in the middle. And then we've got 1 plus 4 plus 5, 10 electrons. So we've got 2, 4, 6, 8, 10. Not going to work out very well, is it? So we need to do some sharing. So let's take this lone pair and make a double bond. We're getting closer. We need to take this lone pair off of carbon and make another bond, so a triple bond. Now we've satisfied the octet rule. How many electron groups are around the carbon atom? 2. So the hybridization is 1, 2, sp. Right? So the hybridization, we've got 2 electron groups. So hybridization is sp. So on the carbon, sp hybridization means that we've got 2 sp hybrid orbitals, and what's left? We have 2 unhybridized p orbitals. Carbon has 4 valence electrons, so we can put 1 electron in each of these. For hydrogen, hydrogen's a simple little fellow. He's just got 1 s orbital. And then nitrogen. Nitrogen is a terminal atom here, so we're going to assume that it doesn't hybridize. So we're just going to look at its regular orbital diagram. S and P, 5 valence electrons. So 1, 2, 3, 4, 5. So nitrogen has 3 half-filled orbitals. That's why nitrogen likes to make 3 bonds. Carbon hybridizes, and when it hybridizes, it has 4 equivalent, or it ends up with 4 half-filled orbitals, and that's why carbon likes to make 4 bonds. So put carbon in the middle, and what do those sp orbitals look like? Two. What did two balloons do? Let's draw two balloons. One will go that way, one will go that way. Those are the sp orbitals. And so one of these is going to overlap with hydrogen. So here's hydrogen with its s orbital. And so that's going to be a pair of electrons. One electron from the carbon, one from the hydrogen. And then over here, I've got nitrogen. Here's nitrogen. And what kind of orbitals does nitrogen have that are half-filled? P orbitals. So it's got a p orbital. That one's going to run off the screen. So that can overlap with the hybrid orbital of the carbon. So carbon actually has 4 orbitals, though. This is 1, 2. Those are the sp orbitals, and it also has p orbitals. So we got to draw the p orbitals. So we got a p orbital going up and down. That's 1 orbital. And then we've got one going in and out of the screen. And for nitrogen, it's got an orbital going up, p orbital going up and down, and one going in and out of the screen. Use your imagination. So there's one electron here, and there's an electron here, and an electron here, and one here. So these are going to form pi bonds. We're going to get side-to-side overlap. So these are going to overlap side to side on both sides. That's the top, the ones that are going up and down. And then the ones that are going to go in and out are going to interact in front of the screen and behind the screen. And that's a little harder to show. Does that make any sense at all? You can see why I didn't go into art, right? I'm a functional drawer. I'm not very good. Okay, let's name these. So this one, between hydrogen and carbon. What kind of a bond is that, pi or sigma? It's a sigma bond. So sigma. And it's between carbon and hydrogen, right? Because here's carbon, here's hydrogen. So we've got carbon and hydrogen, and then we have to identify what are the orbitals that are overlapping. On carbon, it's an sp, and on hydrogen, it's an s. So what about this bond? That's a sigma bond, this purple red one right here. Sigma. What's overlapping from the carbon? The sp. And then it's overlapping with nitrogen. And nitrogen has a p orbital. Let's look at this bond. It's supposed to be just a regular arrow. Pi or sigma? It's a pi bond. It's a side-to-side overlap. So that's pi, and it's between carbon and nitrogen. And what are the orbitals that are overlapping? They're p orbitals. And this other pi bond is the same notation. So this notation for pi bonds, it's always going to be the overlap of p orbitals, unhybridized p orbitals. In the sigma bonds, you'll get hybridization on the central atom, and on a terminal atom, you'll just have s or p overlapping. Any questions? I was afraid there was another one. How many of these are there? Okay, just one more. We can do this. Carbon dioxide. Well, we got to look at the Lewis structure first, right? We've done this one before. Whoops, forgot the oxygen. How many electron groups on the carbon? 2. A double bond, you said that just to get me. A double bond is 1 group. So what's the hybridization? Not the geometry, the hybridization. SP. 2 fingers, SP. Okay? So you've got 2 electron groups on the carbon. So this is SP hybridization. So here's carbon. It's going to be SP hybridized. So there's SP and there's unhybridized p orbitals. Oxygen's not going to hybridize, so it's got S and 3 p's. Carbon has 4 valence electrons, so we'll put 1 in each box. Oxygen has 6. So we look at this, and that looks like a lone pair and a lone pair. And this is going to make a bond, and that's going to make a bond. And up here on this oxygen, we have 2 lone pairs and 2 bonds. Doesn't always work out that way, but most of the time it does. So we're going to get overlap of one of the sp orbitals with a p orbital on one oxygen. And then this one is going to go to the other oxygen. There's another one. And then this p orbital is going to make a pi bond with the other p orbital on this oxygen, and this is going to make a pi bond with the other p orbital on the other oxygen. I didn't draw the second oxygen. So we've got carbon in the middle. SP hybridization, it's 2 groups, like 2 balloons. So draw a picture of 2 balloons tied together at the carbon. Oxygen has p orbitals. So here's oxygen, and we'll line up 1 p orbital with the bond from carbon, and we'll put the other one up here. The carbon also has p orbitals. So 1 up here, and where does the other one go? In and out, right? So hamburgers, right? French fries, milkshakes. Sorry. And so we've got another oxygen over here, p orbital. Now, before I draw the rest of that, let's look at what's going on here. So we've got overlap here, and this p orbital lines up nicely with this p orbital. So we're going to make a pi bond between those 2. Oxygen overlapping its p orbital with the sp orbital from carbon. And then one of its p orbitals is a lone pair. The other is going to make a bond with carbon. Well, the up and down one is already busy bonding with the other oxygen. So we're going to need to use the in and out orbital. Wrong color. So we're going to get side-to-side overlap between those 2. this. So here's the model, the ball and stick model. There's the carbon in the middle and the two oxygens. And so this double bond is oriented the way this bond is, up and down. This double bond is perpendicular, and that actually reflects how it happens to be. Any questions? Now we have to label the bonds. So this one is going to have the same label as that one. What kind of bonds? Pi bonds, side-to-side overlap. And they are between carbon and oxygen. So carbon and oxygen. And what types of orbitals are overlapping? P orbitals. And then we've got one other type of bond. That's this one, which is the same as this one. What kind of a bond is that? It's a sigma bond, again between carbon and oxygen. What orbital on carbon is involved? sp. It's the hybrid orbital. And on oxygen, p. Okay?